Okay, welcome everyone. In the last tutorial, this is the second revision tutorial we do. We did one last week, and last week we did the first two questions, question number 1 and the question number 2. We have already done this question anyway in tutorial number 4 and 5, so you can go back to the solutions in tutorial number 4 and 5 and check the solutions, but we're gonna upload the video again for these two questions in the revision tutorial. Today we're gonna do question number 3 and 4, and they are about literally loaded piles. We have already done these two questions in tutorial number 6, so you can go again to tutorial number 6 to check the solution there, and we're gonna upload the solution shortly after the session today. Okay, so in the third question, we have a 6-meter long free-hit pile. So you need to check here for which situation apply. We do have two scenarios, either free-hit pile or fixed-hit pile. So in this case, we have free-hit piles, and that's embedded in a cohesive soil with a cohesion of 50 kilopascal. We have been given the outer diameter of the pile as 305 millimeter, and the wall thickness of the steel pipe is 90 millimeter. So you can work out the internal diameter from the external one and the wall thickness. We need to calculate the ultimate lateral load and the ultimate bending moments or the maximum bending moments in the system. We have been given the eccentricity as 0.5 for the horizontal load. We need to consider the short pile failure scenario. So here we have long free, we have free-hit pile that's embedded in cohesive soil, and considering the short pile failure scenario, we need to assume no axial load. We need to calculate the maximum stress developed in the pile. After we obtain the value of the ultimate lateral load and the maximum bending moments, we need to calculate the maximum stress, considering only the bending moments, and by considering the axial load as 0. So question number 3 is about short pile failure scenario. Question number 4 is about long pile failure scenario. And the difference is that in the short pile failure scenario, you need to determine what's the value of the maximum bending moments. But in the long pile failure scenario, the maximum bending moments, you need to equivalent it to the yield moment of the pile in the system. So the maximum bending moments will be given as the yield moments on the system. So you only need to solve for the ultimate lateral load in the case of the long pile failure scenario. Anyway, now we're gonna start with the question number 3. And for this system of equations, you can use 3 methods to solve this system of equations to find the unknown variables, ultimate lateral load, maximum and maximum bending moments. You can either, if we go back to the lecture notes where we discussed this material, the lateral, this is the material here, which is the lateral load carrying capacity of single piles and pile groups. Whatever the situation is, either free-hit pile or fixed-hit pile, either in cohesive or cohesionless soil, you have 3 options to solve this system of questions. You can either work out the solutions from the first principle of static equilibriums by finding the equations, finding the variables by forming the equations, and the equations you can form here either from the sum of the horizontal forces on the system or the sum of the moments on the system. So you can form 2 equations, one coming from the sum of the horizontal forces on the system and one from the sum of moments on the system, and you can form obviously another equations from the length of the pile here, which is always equivalent on the case of the short pile failure scenario to 1.5d plus f plus g. Or you can use the derived equations, okay, the derived equations in the lecture notes to solve for H ultimate and to solve for M maximum. And as you can see to solve for H ultimate using these equations. The rest of the variables here, they all given in the questions. C, U, D, L, and E value, they all given the questions. Okay, so you can directly solve for the H ultimate value, and that will give you an accurate answer, the same as the one you will get from the first principle of static equilibrium by forming the equations. Okay, because this equation is already derived from the first principle of static equilibriums of the horizontal forces and the sum of moments on the systems. So instead of using the first principle of static equilibriums and this derived equations, you can use this chart to solve for H ultimate and use this chart to solve for M maximum. Okay, so to use this chart, you need to obtain the value of L over D and the value of E over D. The value of L over D is the length of the pile divided by the diameter of the pile. The length of the pile in our case here is 6 meters, and the diameter of the pile is 0.305, so that's already given. And the eccentricity of the pile in our case here is 0.5, and the diameter of the pile is 0.305, so this is already given as well. So you can intersect the line coming from the x-axis with the E over D curve, and to read what's the value of H over CUD square term. And obviously the value of CU and D are given in the questions. CU is given as underlying the shear strength as 50 kilopascal, and diameter is given as 0.305. So you can solve directly for the H ultimate value without going into the first principle of static equilibrium. But you need to be careful while using the charts, because you're going to do some approximation, and that approximations will be different from one person to another. So you need to be very careful, and you need to be as precise as possible to get the same answer as the one you will get from using the derived equations or the first principles of static equilibriums. Because the one we get here on the derived equation, they are based on analytical solutions, and that's an accurate answer. But the one we got from the chart, it should be accurate, the same as the one we obtain from the derived equation, but because the approximation of people is different while using charts, so that's why we're gonna get different answer from the one we get from the derived equations. And that's why you need to be as precise as possible while using the chart if you want to obtain an accurate answer which is comparable to the one you will get from the derived equations or the first principle of static equilibrium. Okay, we're gonna go to the solution now for these questions. Okay, so we're gonna draw a simple chart to simplify the problem. We have the pile here as 6 meters. We have the eccentricity as 0.5 meters. We have the H ultimate acting at the top of the pile here, and we have that's embedded in a cohesive soil with underlying shear strength of 50 kilopascal. And this is the layout or the cross section of the pile with external diameter 0.305 and shell thickness as 19 millimeter. You can work out what's the internal diameter by subtracting these two values from each other. We have the eccentricity as given as 0.5 meter. So considering the short pile failure scenario, as we said, we're going to solve these questions from the first principle using the first principle of static equilibriums. In this principle, we need to form equations. And one of these equations will come from the sum of the horizontal forces on the systems. If we go back to the lecture notes here, to this slide here, if we go back to this lecture slides, we can see that the sum of the horizontal forces on the systems is equivalent to the H ultimate, the ultimate horizontal load, and the soil reactions. And as we can see, the soil reactions below the F points, below this point here, within the G length will cancel each other. So within G, they will cancel each other because that G over 2 and that G over 2, they are acting opposite to each other. So this reaction force from the soil and this reaction force from the soil will cancel each other. So what we're gonna end up with as horizontal forces is only the soil reaction above this point, which is within the length F, and that will be equivalent to the H ultimate. And if we do that mathematically, what we're gonna have H ultimate as F multiplied by 9 CUD. So that's the equation number 1. And we're gonna get other equations from the sum of moments on the system. The sum of the moments on the system, we need to separate that into 2 parts. The first part, which is above the maximum bending moment points, and the other parts below the maximum bending moment points. Above the maximum bending moment points, as we said, we only have 2 forces, which is H ultimate and the reaction of the soil reactions within the length F. Below the maximum bending moment points, below this point, we only have the soil reaction within the length G, which is G over 2 here and G over 2 here. Okay, so we can form 2 equations. We can equivalent these 2 equations to the M maximum because we are taking the moments about the maximum bending moment points. Okay, so we're gonna end up with equation number 2 and equation number 3 here. And we have other equations as well, as we said before, from the length of the pile. From this chart, we can have the length of the pile is equivalent to 1.5d plus F plus G. So this is equation number 4. If we substitute the known values back into equation number 1 here, because here HU is equivalent to F and known multiplied by 9, CU is given as 50 and D is given as 0.305. So we're gonna end up with a new equations with only 2 unknown values, which are HU and F. And that's what we got here in equation number 5. If we substitute the value of CU as 50 and D as 0.305, we're gonna have HU is equivalent to 137.25 F. And that we're gonna call this equation as equation number 5. And if we combine equation number 2 and 3, the one coming from the sum of moments on the system with each other, after substituting the value of F here from equation number 5, if we substitute the value of F as 1/3 HU divided by 137.25, we're gonna get a new equation. We're gonna call this equation number 6. And equation number 6 is formed by combining equation number 2 and 3 and substituting the value of F in these 2 equations as the one from equation number 5. We're gonna get to a new equations, and that new equations read as 0.9575 HU plus HU squared, the rest of the term, and that will be given with 2 unknown variables, HU and G. And now we're gonna work with equation number 4. Equation number 4 is given as L is given as 6 meter, is equivalent to 1.5 D. We need to substitute the value of D as 0.305 and to substitute the value of F from equation number 5 as HU divided by 137.25 as what we are doing here. Okay, and that will give us a new equation from equation number 4, and we're gonna call that equation number 7, and that will be a function of G and HU. It will have 2 unknown variables, G and HU. So what we have here, we have 2 equations. We end up with 2 equations, equation number 6 and equation number 7. And these 2 equations are with 2 unknown variables, HU and G. And in equation number 7, we have HU and G. Okay, and now to solve this system of equations, we need obviously to substitute one unknown variable as a function of other unknown variables. So what we're gonna do here, simply instead of G in equation number 6, we're gonna put the value of G from equation number 7. So we substitute the value of G from equation number 7 back into equation number 6, and that will give us this new equations, which is 0.957 HU plus HU squared, the rest of equations, and that's by substituting the value of G from equation number 7 back into equation number 6, and that will give us an equations with one unknown variable, which is HU. We can solve simply mathematically, and that will give us a value of 251.715, and that's an exact value. You can get this value directly, okay, without going into deriving equations from the first principle of static equilibriums. You can apply this equation directly. You can apply this equation directly, which is H ultimate as a function of the rest, all the other terms here, all the other variables in this equation, this derived equations are given. If you use this equation here, that will give you the same answer as the one we have just obtained from the first principles of static equilibriums. So after we obtain the value of HU, we need to obtain the value of M maximum. And to get the value of M maximum, we can either use equation number 2 or equation number 3. And to use equation number 2, we need the value of F, because F is unknown as well. And to use equation number 3, we need the value of G, because G is unknown as well. So before solving for M maximum, we need to solve first for F and G. And to find the value of F, we have already obtained the value of H ultimate from the previous step. We can find the value of F from equation number 5, because F here is equivalent to HU divided by 137.25, and that will give us 251.715 divided by 137.25. That will give us the value of F as 1.834. And we can solve for the value of G in the same way. We can use this equation number 7, because we have already obtained the value of F in the previous step as 1.834. So we can substitute into equation number 7. We can find the value of unknown G as 3.71. And then to solve for M maximum, you can either use equation number 2 or equation number 3. That should give you the same, exactly the same answer. If we use equation number 3, by substituting the value of G back into that equation, that will give us the value of M maximum. That will give us the value of M maximum here, and that will be 472.28 kilonewton meter. We can do the same for, after we obtain the value of M maximum, we need to solve for the maximum stress value. And for the maximum stress value here, we can use this equations, which is the maximum stress is equivalent to, because here we only consider the bending stress, we have omitted the value of the axial load into the calculations of the maximum stress. We have only considered, as you remember from the questions, we have assumed no axial load. We have only assumed the bending moments into the calculation of the maximum stress. So in this scenario, the equation to solve for the maximum stress will be equivalent to the maximum bending moments, my, divided by the distance from the external to the axis, where we calculate the maximum bending stress, and that's divided by the moment of inertia on the system. The moment of inertia in the system for the pile, because it's a cylindrical pile, is given in this equations, you already know, which is pi divided by 64. That's multiplied by the external diameter to the power 4 minus internal diameter to the power 4. And that will give us this value, which is 1.75 to the power minus 4, m to the power 4. And if we use these values here, we can obtain what's the value of the maximum stress as 411.56 megapascal. So that's using either the first principle of static equilibriums or the derived equations to solve for H ultimate and M maximums. You can, instead of using these equations, okay, you can directly use the charts. And to use the charts here, as you can see, we can solve directly for H ultimate by using this chart here. As we said before, to use this chart, you need the value of L over D and E over D to find what's the value of this term. And this term, if you found it, you can find directly the value of H ultimate, because you know the value of CU and D square are already given in the questions data. So you can solve directly for H ultimate. And the same apply for M maximum. You can use this chart as well to find what's the value of this term after determining what's the value of L over D and E over D in your questions. So if you use these charts, you can have L over D in the questions, length of the pile 6 divided by diameter of the pile as 0.305 E over D as 0.5 divided by 0.305, and that will give us 19.6 and 1.639. If we go to the respective chart, you can see that the value of 19 here, 19.6, if you draw a vertical line until you cross with the respective 1.6, and you can see in our case here, in this particular case, the crossing of these two curves will be somewhere out of the range. So you need to do some approximations, but you need to be as precise as possible to make reasonable approximations for the value here. Okay, considering this scale, obviously. Okay, so the value will be cross somewhere here with the 1.6, because this is the two curves between 1 and 2. So 1.6 will be somewhere here. So this value is about 55. Okay, and that's what we have done here. We put this value as 55. As we said, you need to be as precise as possible, because that will affect the calculated H ultimate value. And using this formula, you can find what's the value of H ultimate by working out the value of Cu as 50 and D as 0.305, multiplying by 55. That will give you H ultimate as 255.82 kilo in newtons. If you compare the value obtained of H ultimate from the chart with the value obtained directly from the derived equations from the static equilibrium principles, you can see that the values are somehow different. They are not much difference, because we are precise in the calculation of this term here. This one is more accurate because it's coming from the analytical solutions of the problem. This one is an approximations, and as we said, it will be different from one person to another, but it shouldn't be that much difference. So you need to be as precise as possible. Okay, so if you assume this value as 56, 54, 57, that should be fine, but not as 75 or 80 or 40. That will be out of the range. So that will be obviously incorrect. So you need to be as precise as possible, as we said, because you need to be as approximate as possible to the actual or the accurate solutions coming from the first principle of static equilibriums or the derived equations in your lecture notes. As we did with the H ultimate value, we can do for the M maximum. You can either use this one of these derived formula, okay, to find what's the value of M maximums, or you can use the another chart. The another chart is for M maximum. So you can read what's the value of L over D, 19.6, as we said before, with intersected with the E over D curve, 1.6, and that will give you the value on the y-axis of this term here. Cu and D again are given, so you can solve for M maximum directly. Again, the value will be different from the one you obtained from the solution here, from the equation here, because that is an analytical solution, but that's not. The charts are based on these equations, but the approximation of people is different. So that's why you will get a different solutions, okay? Because you are approximating the points differently from one person to another. Anyway, that's the value of obtained value from the chart, which is 483. As you can see, it's different from the value obtained from the equations, from the derived equations here. If you use this value to find the maximum stress value, you will find that the maximum stress value is 421.21 megapascal. If you use the derived equations or use the charts, both answer will be correct in the exams, but using the chart, you need to be as precise as possible, okay, to get an accurate answer. So that's for question number 3. Now we're gonna do question number 4. Question number 4 is assuming the free head pile failure scenario, but in this case we're gonna have long pile failure. Okay, so instead of short pile failure, we're gonna have long pile failure. So we're gonna have a plastic hinge point, as we can see in this chart in your lecture notes. So this is the failure scenario apply. As you can see, we don't have any soil reaction below the plastic hinge point. So this is the main difference here in our case here. And the value of the maximum bending moments here, we're gonna equivalent it to the maximum yield of the pile material, because in here we have M maximum is more than My, so we're gonna equivalent these two values with each other. So the value of My will be given as M maximum, so that will be known, not as with the short pile failure scenario. So the only unknown value in the long pile failure scenario will be the H ultimate value. And as you can see, you can form two equations here, or two system of equations from the first principle of static equilibriums. One coming from the sum of the horizontal forces on the system. The horizontal forces on the system are the H ultimate and the soil reaction within the length F. The soil reaction within the length F is equivalent to 9 CUD multiplied by F, and that will be equivalent to H, and that's equation number 1. As you can see, this is equation number B, we call it here. And equation number A is coming from the sum of the bending moments on the system. The sum of the bending moments on the system, they are according to the, the sum of the bending moments on the systems, they are according to the two forces on the system. So there are moments coming from the H ultimate, there are another moments coming from the soil reactions, and we have the my on the system here. So the moments on the system about this point should be equivalent to the my value, which is given as 430 in our case here. So we can form the another equations from the sum of the moments on the system about the plastic hinge point. So we're gonna have two equations. We're gonna call them A and B. And in these two equations, as you can see, we only have two unknown variables, which are HU and F. So we can simply substitute the value of F as HU divided by 137.25 back into equation number A to solve for HU value. And that's what we have done here. We substitute the value of F from equation number B back into equation number A, and we solve for the HU value, and that will give us 236.42 kilonewton. So that's using the first principles of static equilibriums, or you can, as well as what we have done with the short pile failure scenario, you can use the derived equations directly. The one we derived here, that's for the long pile failure scenario. You can use this equation directly to solve for the H ultimate value. Cu is given, D is given, E is given, and My is given. So you can solve for H ultimate directly, okay, using these equations, and that will give you the same answer as you get from the first principle of static equilibriums. Or you can use this chart to solve for H ultimate. As you can see, My over CUD cubic is given. Okay, this value is given, and E over D is given as well. E as 0.5, D as 0.305, My as 430, Cu as 50, D as 0.305. So you can find what's the value of this term in the x-axis, what's the value of this term on the E over D curves. You can read what's the value of H ultimate over CUD square. By knowing this value, you can solve directly for H, but again, you need to be as precise as possible in using the chart in approximating the value of intersections of the points on the system here to find as accurate value as the value you will get from the derived equations from the static equilibrium principles, okay? So you have three options to solve this system of equations, the lateral loaded piles. You can either use the static equilibrium principles by finding equations from the sum of the horizontal forces on the system, or the sum of the moments on the systems, and the length of the piles, obviously in the case of the short pile failure scenario. Or you can use the derived equations we have already worked out in the lecture notes, or you can use the charts, okay? So you have three options to solve this system of questions. Thank you for joining me today, and hope you all the best.